he'd ask questions. Like, oh, yeah, it was kind of nice. Anyway, yeah, what do we call an acid that is not in an equilibrium state, but just dissolves completely and becomes completely a strong acid? Good. So in the case of a strong acid, we start with.
Sorry to interrupt.
Are you really?
I also forgot to mention that Michael Cowan placed an amazing second place in the 400 meter, so he will also be moving on to salsa next week.
So a strong acid just dissolves completely. You put it in water, and 100% of it becomes negatively charged, and it releases its H+ ions. And we did a little bit of review of grade 11 acid-base chemistry just using that. But most acids exist in an equilibrium state. In an equilibrium state. And in an equilibrium state, it means that the acid will give up its hydrogen. That's the definition of an acid, according to the Bronsted-Lowry theory of acids, right? And if you read about that, in the old, what you'd been taught in grade 10 and 11 and 9 is what we call the Arrhenius theory, which is that acids give up H+ ions and bases give up OH- ions. In the more kind of grade 11 chemistry thinking, that worked. In grade 12 chemistry, we're now talking about equilibria. We need a slightly more complex system. So we use something called the Bronsted-Lowry theory, which basically says that any acid is something that gives up a hydrogen. And you can see here this acid has some hydrogen on it that it's going to donate. That makes it an acid. A base is anything that can receive that H+ ion. That H+ ion actually has to go somewhere. And in this case, the most common base is just water. So what will happen is the acid will give up its H+, the water will take it. And now we have a negatively charged A-, that acid having given up the H+, and we have H3O+. But because it's in equilibrium, this reaction can also go the other way. Well, if H3O gives up an H+ to become water, that makes H3O an acid, because anything that can give up an H+ ion is an acid. So in any weak acid where we have an equilibrium, the acid, once it gives up its hydrogen, will become a base, will become something that is ready to accept an H+ ion. And the water, which we thought of as the base when it was receiving the H+, is now H3O+, and that is now ready to behave as an acid. And the reaction can go in the reverse direction. Does that make sense? It's really no different than any of the other equilibria we've talked about this unit, but we're giving them specific names. Acids deserve sort of specific names. But long story short, this reaction can go forwards, and it can go reverse. It exists in an equilibrium state. And if it exists in an equilibrium state, then we can write an equilibrium law for it. We can write an equilibrium equation. And you'll notice there are 4 species in this reaction, but only 3 in the actual equation. Why is that? Yeah, so the concentration of water in water is a really big number. It can be measured. It's just how many moles of water make up a liter of water, but it's a big number. And in any reaction you're dealing here with weak acids and bases, the change, the X value when we go to change these things, is going to be relatively a very small number. So small that to any meaningful number of significant digits, that concentration of water isn't going to change. It's going to be a constant. Because even though it is changing, it's like when I go take, if you go take a 2 ounces of water out of your swimming pool, have you changed the volume of the swimming pool? Not appreciably, right? Yes, if you're measuring very, 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 very accurately, you could measure that difference. But in terms of, if you had, I have no idea how much water is in a swimming pool. Full disclosure. A couple thousand liters? Does that sound like a ballpark. Long story short, if you have a couple thousand liters of water in the swimming pool, taking out a couple ounces, 50 milliliters, does not meaningfully change that number. You wouldn't then have to go say, oh, the volume of my swimming pool has changed. For all intents and purposes, it hasn't, right? Does that make sense? So we are able to exclude that here. And this is not a cheat. As long as we are measuring to fewer significant digits than how that concentration of water will change, it will not affect our math here. Cool? All right. So we said that for any acid then, its equilibrium constant is just the concentration of the dissociated acid, which is the conjugate base, multiplied by the concentration of H3O plus, divided by the concentration of the acid that has not had its H plus taken away. Products divided by reactants. We don't have to worry about water. Because the products are on top, the bigger the Ka value, the more the acid dissolves. Does that make sense? A really, really low Ka would mean that this acid doesn't dissolve much. A really, really high Ka would mean that the acid dissolves a lot. Does that make sense? And so if we look at this table, we can see that they range from just to the -2. Chlorous acid is relatively strong. Acetic acid, which is just vinegar, relatively weak. And everything else is kind of somewhere in the middle. Oh, we have a really weak one. What is the really, really weak acid on here? Other than water. Yeah. Hydrocyanic acid is just times 10 to the -10. Very, very weak. Does not dissolve much at all. And we have another one, phenol. All right. So we said, if all we want to know is, what would the pH be if I dumped some water into or some acid into water, rather? We can do that using an ICE table, just like we've been doing. And we went through one example with that yesterday, yeah? I want to do another one today, and I want to introduce you to a shortcut that you can make. And I want to double check my number here, because sometimes I lie. But so if everyone can get on this, this is what, the 3rd page? Let me just double check my notes quickly, because I have lied about this before, and I would feel guilty. Yeah, the 3rd page. It's section 4. Okay, 500. So we have kind of an arbitrary rule here. And it's going to let remember that for any acid, its equilibrium constant is just what? For any acid, what goes on top? What goes on the bottom? Oh, I've drawn one too many. You can tell me where I put one too many too. Okay. And what's going to go in these? Yep. Yep. And what is that? A negative. Because when you do this with real acids, of course, you're not going to see A. Like A just literally stands for acid. But that is the acid after it has lost its hydrogen. So we actually call that the conjugate base, right? Because it's now ready to behave as a base. Once an acid gives up that hydrogen, it now can't behave like an acid again. It doesn't have another hydrogen to give up, unless it does, which can happen. But it's now ready to act as a base. It's ready to receive a hydrogen. Okay, multiplied by? Yep. And we are usually going to, from here on going forward, write it as H3O plus. Though you're right, it's the same thing. It's that hydrogen having left. And on the bottom, oh, Concert program. Yep. Yeah. Very good. Now, here is, since this is true, one thing we can say is this. If HA is really big, Ka will be small. Does that make sense? And if that distance is big enough, if the concentration of HA is big enough and the Ka is small enough, when you do the math, you'll get this very lucky thing where when you do all the math and you solve for x, x will also be much, much smaller than the original concentration of HA. Does that kind of make sense? So you'll go through, you do all your math, and if Ka is really small, x will end up being small, right? Because x squared is on the top. Can you kind of picture that? If that difference is big enough, when you subtract x from the original HA, it won't really change. Does that make sense? So if HA is big, Ka will be small, and then x will be small. And if that is true, the concentration of HA minus x, which is going to be one of your columns at the bottom, right, will just be, for all intents and purposes, the concentration of HA. Long story short, if you're dealing with weak acids in high concentration, the concentration of HA minus x that you're going to have to deal with, that makes it ugly because that's the reason we have to do a quadratic, right? Because you've got that bracket. So that ends up being the reason why you have to do the quadratic equation. Well, if that difference is big enough, this difference will end up being really small. And you can just say that concentration of HA won't appreciably change. And here's the test for it. If the concentration of HA is 500 times bigger than Ka or more, then to 3 significant digits, it won't change the concentration of HA. That make sense? So as long as you're working with less than 3 significant digits, if the concentration of HA is 500 times bigger than Ka, then we can say the concentration of HA minus x is just the concentration of HA. And that will make our algebra much, much, much easier. I think this will make more sense to you if we go through and do an example. But it's a time-saving assumption we can make. So, okay. So we are going to take we're going to do 2 of these guys here, and we're going to love it, okay? So we are going to take H3PO4, and we're going to dissolve it in water, and what are we going to get? Yep. Really good. And? Very good. Does that make sense? Now we're going to do all the math for that. And then once we've done that, oh, and of course, I've drawn a straight arrow. Was that smart? No. Is this a strong acid? Let's go check from a strong acid list. Oh, where is our strong acid list? Oh, it's right at the top. Is phosphoric acid one of our strong acids? No. So this is not a straight line. This should be an equilibrium, right? Okay. So this is the first thing we're going to do. And what am I going to put in my table here? H3PO4. Good. Then? Yep, and? Great. And again, I didn't include water because water is essentially constant in all of this. All right, now, when we first drop this in, what's the concentration? I gave you a lot of numbers on here. But what's the initial concentration? Anyone have any idea what the concentration might be? Yeah. Good. Okay. So I wasn't trying to make that. By the way, instead of writing moles per liter, what could I write? Yeah, molar. I could write big M. Same thing if you prefer moles per liter. Go nuts. So what I want to imagine is this. I have some solid phosphoric acid and a liter of water. I measure out 3.5 moles of the phosphoric acid. I drop it in. All right? In that case, when we first start off, how much of it has dissociated and become the conjugate base and H3O plus? Not a trick question. Before, when I just put it in the water, before anything has happened, what will the concentrations of these be? Yeah, does that make sense? All right, now talk to me. What is going to happen? As they actually dissolve, they're going to start dissolving, and this forward reaction will happen. But then, of course, the reverse reaction will happen as well until eventually they will settle into an equilibrium state where they are dissolving at the exact same rate they are recombining, and everything will reach a steady state. How do I fill out the change column here in the meantime? How will this change over the course of reaching that equilibrium? Well, from the initial state, is the concentration of the undissociated phosphoric acid going to go up or down? It's got to go down, right? How much will it go down by? Yeah, we don't know. So we're just going to say it'll go down by X. But as it is used up by X, what will happen to the conjugate base? The H2PO4 minus. It should increase by the same amount, because if we look, it's a 1-to-1 stoichiometry. 1 mole of everything in this reaction, right? What about the H3O plus ions? It'll go up by X. Does that make sense? Now, here's where we can go to the side. Normally, I would have to say what here? The final concentration of this will be I would have to say 3.5 molar minus X, right? But here's what I'm going to test. Does that make sense? We start with 3.5 molar. It's going to go down by X. We can test our assumption. Because if the concentration of HA is 500 times bigger or more than the Ka for this acid, then we can say that this will still just be 3.5. That the change will be so small that even though it is going to change to 2 significant digits, it will still be 3.5. Does that make sense? So let's go to the side and test that. And all we do is we just do concentration of HA divided by the Ka for this reaction. And the concentration of HA is 3.5. And what's the Ka for H3PO4? What is it? Yeah, what's the one for H3PO4? That's the acid we're talking about right now. Like that? Cool. All right, so do that math. How much bigger is that than that? Are the calculators in here? I don't know what the calculators are. You can use your phone. What do we get? Oh, maybe I will try to grab the yellow calculators because scientific notation is miserable on your phones, isn't it? If you can't do scientific notation, of course, you could just write this in standard notation. That would be 3.5 divided by what? 0.007, right? And what do we get? Try it again, because my instinct tells me we should get a really big number, because we're dividing by a really small decimal. How much? That should be down here, 7.0 times 10 to the negative 3. Use the first Ka, because we're using the Ka for H3PO4. But your process is good. And what do we get?
Sorry for the interruption, staff. All those students in Mrs. Cook's grade 9 girls and boys phys ed classes
Is that what you got?
are going on the trip today. If you can please make your way down
7.0 times 10 to the negative 3.
The bus is now here.
What'd you get? 500? Okay. And you can see that I picked this one very carefully, these concentrations. So this just passes, but it passes the test. All right, so this passes the assumption test, and it tells us then that X is going to end up being a pretty small number. In fact, so small that 3.5 minus X is going to be 3.5. That within our number of significant digits, this number isn't going to change. Does that make sense? Tell me if it doesn't. What that lets us do for this table is beautiful, because we don't have to say that. We can say that this is just going to be 3.5. And that is going to make solving this a whole heck of a lot easier. Because now, what will go in these spaces? Well, it'll go here. Wow, this isn't going to change, but this is going from 0. So it is going to, this X will matter. So what we're saying is we're going to be drawing from a well that's really, think of it this way. If you are dying of thirst and you take a cup of water out of an amazing oasis stream, have you appreciably changed the volume of that oasis? No, you've just taken one cup of water. But does it make a difference to you? Huge difference, right? That's what we're talking about here. This isn't going to change because X is really small, and it's going from being a really big number. But this is going up by X, and it's starting with nothing. Does that change matter? Does that make sense? So this, we are able to say, will still just be 3.5. But this will still be X. And this will still be X. So this assumption is just going to make the algebra easier. And in fact, I am going to do it with 3.5 minus X on the side while you do it the easy way. And I'll show you that we should get the exact same answer because that X is small enough. So now when we actually want to solve for X, what are we going to have to use? We want to know the ending concentrations of this. We've set up our ICE table. Now what do we do? Good, give me one. Yeah, I'm going to put Ka, and I'm going to specifically say H3PO4 is equal to yep, so Very good. And on the bottom? Very good. All right. So I want you to plug your numbers in and solve for x. And again, this won't end up being a quadratic. This will end up being a case where you just get to take the square root, which is nice. Taking the square root is a lot nicer than solving a quadratic equation. And help one another out. Don't be shy. Sorry? Give it to me again. This is for H3PO4. You're not using it for your x, you're using it for your Ka, right? So what we'll say here is we will say 7.0 times 10 to the negative 3. Is that the number? Yep. Is equal to x times x divided by, what did we say this is? 3.5. And I'm going to exclude the units there for simplicity's sake. So we already tested this number against that to say that 3.5 isn't going to change appreciably, but that's still the number we use. Okay? I know. Okay, have we got the answer to this? All right. So how did you approach this? What do we do? Sorry? Yep. So what'd you do? Which gave you what? Okay. And that's equal to x squared. Good. And then to actually solve it, we can say x is equal to. Okay. And that gives us what? 0.156. Okay. Now, I want you to note, would that change this to 1 sig fig? Well, it would, right? It would make this go down to 3.2, or 3.3 rather, to 1 sig fig. But, so it's not a great way to get the concentration of this, but note how your answer compares to the one I got using the quadratic equation. They are marginally different, right? But for the purpose of this, we're trying to find the pH, it's close enough. Does that make sense? So you are making an assumption, and anytime you make an assumption like that, you are going to get slightly inaccurate results or slightly imprecise results. But for finding the pH, that's considered acceptable. Does that make sense? Okay. So now we know what x is equal to, 0.156. And so we can come up here and put that in our table. Does that make sense? Does anyone have any questions about that? We got all the time we need, and I will talk through it 7 times if I need to. Is there anything in any of that people don't get? Now's the time to ask. And you probably, if you're thinking it, there's probably 6 people thinking it. I'm good to move on? Yeah? Yeah, we should, which would make it 0.16. Yep, they are different. They're different to the last significant digit. So again, anytime you make an assumption, you are giving up some of your precision. And you'll notice, I picked this one very carefully to be right on the line. We say 500 times bigger is the absolute cutoff. And the difference in our answers was the rounding on the significant digit. Does that make sense? So the absolute cutoff, we said, is 500, and to 2 sig figs, that can potentially cause a rounding error on the last digit, which we are going to consider an acceptable amount of inaccuracy. Does that make sense? If you wanted to be more stringent, if instead of 500 you made the standard 1,000, you would never get that rounding error on 2 sig figs. Does that make sense? Okay. Any other questions about that? I now want you, H3PO4 has how many hydrogens that it can potentially give up? 3. We've looked at the first hydrogen, and we found its equilibrium state. But now I want to look at the second hydrogen. And if I want to, we could even look at the third, though we're not going to today. Does that make sense? Now, here's the thing. Go look at the Ka for the second hydrogen, for H2PO4. What do you notice about its Ka value? Much smaller, right? So it is probably not going to appreciably change our first equilibrium. Does that make sense? How could we test that? How do we test the assumption that it will not appreciably change our second Ka? Well, let's look at this reaction here, Jade. This second reaction is going to be starting off with the H2PO4. And what's going to happen to it? Oh, what am I doing? I don't know what I'm doing. To lose a second hydrogen, we would end up with what? Well, what's this thing going to look like if it gives the hydrogen up? Yeah, 2 minus, because it's given up another plus. And that will go to another water as well. Does that make sense? Okay. Now, keep in mind that this is also involved in our last equilibrium, right? So this has the potential to screw our last equilibrium equation up. But the Ka value is so small that this is going to happen in very low amounts. Does that make sense? The first one already happened in pretty low amounts. This one is going to happen in very, very low amounts. This is not going to make a whole lot more acid, but it will make some. Anyone have any questions about that? You have to do the first equilibrium before you can do the second one. In the first equilibrium, we figured out how much of this stuff we had. Does that make sense? Now we can use that to figure out how much of this stuff we'll get. Does that make sense? Okay. So, what are my column headings going to be here now for this equilibrium? H2PO4 negative, the concentration of, and yeah, and the last one, okay, now I want you to be careful. We're going to fill this in, okay, but I want you to be careful because remember, this is coming from this has happened. That makes sense? So how much H2PO4 do we have after the first equilibrium has been established? So this first equilibrium happens. We take the H3PO4. It gives up a hydrogen. What does it become? H2PO4 and H3O plus. So what are we starting with here now? This is picking up where the last equilibrium left off. So how much H2PO4 do we have? Very good. And how much H3O plus are we starting off with? How much H3O plus are we starting with? What do you think? Is this just starting off in plain old water? No, we said this equilibrium happens. It picks up where the other one left off. And where the other one left off, how much water do we have? Or how much water? How much H3O plus do we have? Good. Okay, and that's the big takeaway here is that sometimes we start off in equilibrium that does not start off at zero. Yes, ma'am? It's yesterday's. Were you here yesterday? Yeah, we are on the third page of yesterday's. And let me know if you're missing it. I can grab it for you. The only thing we aren't starting with here is any of this. So this reaction, we're going to be making more H3O plus, but we already have some H3O plus to begin with because it was made by this reaction. Does that make sense? All the same, that doesn't affect our change conditions here, which is, what is this going to do? As we go through this reaction, this is going to get used up, right? So what will its concentration be? It will change by negative X. Good. What will happen here? It'll increase by X. And here, also increase by X. Now, if we want to make our math simpler, we can always test an assumption. What is that assumption? This should be 0.16 minus X, right? But what can I check on the side? Yeah, to see if it passes the assumption test. So let's take a look. How do we see that? What is our test? Great. And what are those numbers? So the starting conditions, we just test those concentrations. What concentration are we starting with again? Was it 0.16? So we're starting with 0.16 molar. And what's the Ka? for this one? Okay. And if you're trying to punch that into a crappy calculator, that'd be 0.16 divided by 0 decimal, and then 1, 2, 3, 4, 5, 6, 7, 6, 3, like that, right? I have a feeling this is going to be a lot bigger than 500. Can you punch that into your calculator and confirm it? And what this is going to mean is that phosphoric acid loses a lot of those first hydrogens, but it doesn't lose many of its second hydrogens. That's not something that happens a ton. What do we end up with? I think it's something, it'll be on the order of like, I don't know, somewhere between 100,000 and a million, I think. That's one order of magnitude. Come on, I've got the order of magnitude, I think. That's pretty good. Try this out. Let me know what you get. 7 zeros. Come on, we don't have all day. Does that have a scientific notation button?
Probably.
I have an E button that I use, and I don't even know what it is.
It's right there.
Sure, that's
Oh, it's 2 million. Whoops.
Yeah. Oh, no, that's different. 2.5.
I'm like,
Okay. So that number is really, really, really big, which means this passes the test. Hey, you passed the test. And what that means is that even though this should be 1.16 minus x, what can we just say the final concentration of this stuff will be? Yeah, we can say that it's safe to assume that that is not going to change much because it passed the test. By the way, if 0.16 minus x isn't going to change, what about 0.16 plus x? Would it make any sense for that to be radically different? If subtracting x doesn't make a difference, does adding x make a difference? So we can say that this number will just be 0.16. Hey, what's the only thing here that's going to change appreciably? That guy. Yeah. Cool. Go ahead and solve for x. By the way, if we got some crazy number for this, we would actually have to go back and redo our first equilibrium. Can I mention that? If this number had changed a lot, if this went from being 0.16 to being 0.07 or something, that would actually affect our first equilibrium, and we'd have a mathematical nightmare on our hands. Luckily, this isn't going to change significantly, so we don't have to think about how this equilibrium affects the first one. Is that, why does it make any sense? I want it to have. If wishing were able to make it so. Oh no. Yeah.
costumes. And I made it out at for Alice. Can we do that at some point today? Have school lunch. You're thinking that way, you know.
Yeah. That works for me. So yeah, come see me over. Okay.
all right.
Where's that from? Yeah, absolutely. Yeah, you can. Was that a pen drop? Yeah, the math ended up being easy on that one. Had to happen eventually, right? And is that number, were we right? Like, is that number being x going to appreciably change that? Not the slightest bit. We'll appreciably change that. Not at all, right? Does that make sense?
Yeah.
And now you can go back and look at what the original question was. And the original question was, what is the pH? Which we know pH because it's going to be based on that, which we actually knew all the way here. See, so that second hydrogen that phosphoric acid has is so unlikely to dissociate that it doesn't even change the pH of the solution compared to if it wasn't there at all. And we could go through and do another one of these for that third hydrogen, and what do you think you'd see? Even less chance. Especially because Le Chatelier's principle tells us that having lots of this is going to push this reaction in which direction? In that direction. So the fact that we made a lot of this here means that when we get here, this reaction doesn't want to happen. It doesn't want to associate with this is already really hot. That was Shad. He's the guy. He's the principal for a reason. He went to principal school. Did I have a school? I don't know anything about becoming a principal. I think given that this is my career, I know something about that, but I don't know. Me? Oh my God, no. Could you imagine a school that I was running? It would be chaos. Listen, nobody's a bigger fan of me than I am, but that would be a bad idea. I say that I used to like it. Isn't that nice? Easiest math yet. So x is going to be equal to? There you go. That's it. Right, you see that there? We have 0.16 divided by 0.16. Well, what's 0.16 divided by 0.16? No! False. It's just 1. And so you actually end up with 1x equals that. X equals. This one's really nice. All right, so, oh, that's red. I don't want it to be red. Okay, so the Ka of H2PO4 minus, the equilibrium constant of getting rid of that second hydrogen is going to be equal to the concentration of the second conjugate base times H3O plus divided by H2PO4 minus, which is actually our acid in this case. And what we should end up being able to say is, what is the actual Ka? 6 point something?
6.3 times 10 to the power -8.
Really good. Is equal to 0.16 times x divided by 0.16. And so we end up in the very nice, easy situation of these dividing by one another and canceling. And so we just get x equal to 6.3 times 10 to the -8. Basically what it means is that we have so much H3O plus already. We have this already that we end up with just that value for change. And now we can answer the original question. And what was the original question? Okay, so one of them is pH. Now pH is easy. It's the negative log of concentration of what? H3O plus. Good. Oh, good Lord. Okay, there we go. That was weird, right?
Yeah.
That wasn't just me. That was really strange. All right, so in this case, that's the negative log of 0.16, which hasn't changed since our first equilibrium, right? And that should be on the order of 2. What do we got?
1.79.
Really? Oh, what's wrong with me?
If Caleb was here,
Right.
you wouldn't hear the answer.
Caleb, if you're listening to this right now, you're right. I'm always off by 1. I'm sorry. So 0. 0 point what? 7958. So 0.80 if we're going to 2 sig figs. Oh, we're just down to P now? I don't know. Do you think Caleb is like logged into my Microsoft account and is modifying my note? I did that to Cleves once last semester.
Remember when we sent him a picture?
Yeah, we threw a picture into his note. It was very fun. I had a good time. He did, yeah. It's so tempting. I have access to all of his notebooks this semester, and I haven't because, of course, I don't know any of the students at his school, and I don't want to be rude. But, well, I think it'd be very funny. But I did change one of his tests and put a really funny question in it one day, and he didn't notice and printed it, and I was proud of that. Like his Unit 2 grade 11 college maths test. I took the question he had, but I just made all the names in it really goofy, and I made it like really like one of my classic like simple question that takes up half a page because the writing's really over the top. Exactly.
Took up an entire page. And it was like 3 numbers.
And it was the easiest question you'll do all year. Okay, so that was one of the things. That was one of the things I asked for. What else did I ask for? Concentration of H2PO4. Yep. Yeah, if you go read the top. Concentration of H2PO4. And the concentration of HPO4, 2 miles. And those are easy too. They also come right from the table. What are they? .16 moles per liter. And this one, very good. Good job, guys. These aren't so bad, are they? That is the worst case scenario I could possibly give you. An acid that has multiple hydrogens to give up and ask you to go all the way through it. That's not that bad, right? You just have to plug your way through it. That really is, like, I guess I could be even nastier and give you the Ka for the third hydrogen and say figure out those concentrations too. But that really doesn't change all that much. It'd just be yet another step of the same. Yes, ma'am. Yep, please. This assumption?
Yeah.
Okay, here's the deal. Basically what we're saying is, see how small x ends up being? It ends up being this tiny number. And so in fact, when I go to subtract 0.16 minus x, it ends up just being 0.16. Now, the thing is, if I'd known that in advance, I could have just said, oh, shoot, I don't have to have x's here because it just is going to end up not changing. Is there a way to predict when that x is going to end up being really small? And the way we predict it is we say, she's asking for my attendance. We say you can look at the concentration of the acid you start with and divide it by Ka. And if HA is 500 times bigger than Ka, then HA minus X will just equal HA. The X will be small enough not to change it. And so all we do is we divide HA by Ka, and if that number is 500 or bigger, then we say, I can ignore that X. And in this case, we actually got a twofer. This doesn't always happen, but if 0.16 minus X passes the test, and it's just going to stay 0.16, well, then obviously 0.16 plus X is also not going to change. Now, on the other hand, 0 plus X, well, that's going to change because any change from 0 matters. And the analogy I used, I don't know if you're here, is like, if you think of it this way, if you were dying of thirst and you finally stumbled across a lake and it's full of water, and you take your cup and you fill it up and you drink from it, you haven't changed the volume of that lake for all intents and purposes, right? Yes, I took 200 milliliters out of it, but does that matter to the lake? Not a bit. Does it matter to you? A lot. And so that's the same idea here. That X value doesn't change the numbers that are really big, but it changes very meaningfully the number that started off at 0. And in the previous example, we were only able to make that assumption for one place, right? We were able to say, oh, this 3.5 isn't going to meaningfully change. but these guys will change. Does that make sense? Okay. Now, one last thing. Our new Bronsted-Lowry theory of an acid says that an acid is anything that can give up an H+. And a base is anything that can gain an H+. Oh, hey, even in the purest of water, what could behave as an acid? What could behave as an acid even in a cup of pure water? Water, right? If I take water and I react it with water, what can I get? I get, by the way, that this is a little weird. But what's going to happen here? One of these waters can behave like an acid, and the other one can behave like a base. And this, if it behaves like the acid, what's it going to want to do? It's going to give up one of its hydrogens, which will leave it as an OH- ion. And this water is going to behave like a base. It's going to take that H+ ion, which will then make it H3O+. So even pure water actually has some mildly acidic tendencies and mildly basic tendencies. Oh, and they perfectly cancel each other out because it's equal parts acid and base. But this behaves like an acid, and this then must be its conjugate base. If this reaction were to go in reverse, that OH- would act as the base, right? It would be ready to receive an H+. And this behaved as the base, which means that this is its conjugate acid. Good. And over the next few days, we're going to get used to using that language. Today we're going to answer one of what, to me, until I learned this, was one of the great mysteries of science, which is like, why the hell is the pH of neutral water 7? What does that number mean? Because what would the KEQ of this be? For this reaction, what is the equilibrium concentration? Or the equilibrium statement, rather. What do we got? What would it be? Yep. Good. And of course, I could just write that as H2O squared. Good. That make sense? Now, do you think in a cup of water that much of the water does this? What do you think? You look at a cup of water, do you think that an appreciable amount of the water breaks down into ions? No. In fact, we don't have the Ka to test it yet, but I'm going to tell you that this would very much pass our assumption. In other words, this concentration of water is going to be essentially constant. Does that make sense? This is only going to happen a little bit. We are having tech issues today, boy. This does not change appreciably. And so we can just put it in to be part of the constant. And so we name a new constant. And what do you think we call the constant of the dissociation of water? K, W. Did I put that above? I did. And it's just the concentration of, and we wrote it OH first, but usually you see it written this way. And at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14. Hey, how many steps on the pH scale? 14. Think that's a coincidence? Now, the neat thing is this. If you start with everything else being equal, this will actually work out to the concentration of H3O plus being equal to the concentration of OH minus, and it will be 1 times 10 to the negative 7. Because 1 times 10 to the negative 7 times 1 times 10 to the negative 7 equals 1 times 10 to the negative 14. Hey, what's the pH of neutral water? 7. So neutral water has a pH of 7 because it has a concentration of H3O plus of 1 times 10 to the negative 7. Now what this means is this. We can always find the concentration of OH minus in water given the H plus or vice versa. So let's say we have a shampoo. We want to determine pH, pOH, and the concentration of H plus in a liquid shampoo that has a hydroxide concentration of 6.8 times 10 to the negative 5. Basically means this. Water always must balance its H3O plus with its OH minus. So if we get lots of H3O plus, what will happen to the OH minus? It must be low. And if we have a very low amount of H3O plus, what will happen to the OH minus? It'll have more. Does that make sense? Okay. So we can always, if we know the pH or if we know the concentration of H3O plus, we can figure out what water's OH minus concentration will be to balance it out. And it's as easy as using the Kw. Kw equals 1.0 times 10 to the negative 14. And it equals the concentration of H3O plus times the concentration of OH minus. That's always true. So how am I going to do this question then? Yeah, this is just good old-fashioned, Caleb isn't here so I can say it, plug and chug algebra. Let's put your numbers in, solve for it. What do we know from the question? Good, which is actually what number? Beautiful, and where's that going to go, someone else? That's the hydroxide concentration. So in our Kw equilibrium, where does that go? Yeah, it's going to go right here. So times 10 to the negative 14 equals the concentration of H3O plus times 6.8 times 10 to the negative 5. What would I do then if I want to solve this? Yeah, I want to isolate this, so what am I going to do? Divide this by 6.8 times 10 to the negative 5. And of course, what I do to one side, I do to the other. And I should get something on the order of something times 10 to the negative 8. 9? 10? What is it?
1.47.
10 to the negative 10? Cool. Okay. Now, have I answered the whole question? No, I've got part of the answer. What do I want next? pH, how will I do that? Negative log of concentration of that'd be 8 point something, 10 point something. I don't know. My brain's not working today. I'm all sleep deprived. You'll have to excuse me. What do we get? Oh, yeah, that's true. It's very close. And what's the last thing I asked for? This is a new one, I think. Have we talked about pOH before? What do you think it is? If the pH is the negative log of the concentration of H plus, pOH is probably going to be pOH. pOH. What do we think? If you had to guess, hypothetically, is there something you might like focus on? pOH is just, if pH is the power of the hydrogen ion, pOH is the power of the hydroxide ion. So pOH is just the negative log. It's the negative squiggle of the concentration of OH minus, which means it's going to be the negative log of, in this case, what? I think it was given in the question. This will be 5 point something, or it won't be with my track record today. .167, so we'll call that 4.17. There we go. So once you know H3O plus, you can find OH minus. Or if you know OH minus, you can find H3O plus. And you can always find the log, the pH and the pOH. And what do you notice about these two numbers? Something should jump out at you about them. Sorry? Ooh, interesting. Coincidence, but true. Something that isn't a coincidence. What do you notice about them? All you mental mathletes, you. Yes, Zach Brown.
They add up to 7 or 14?
Yeah, pH and pOH always sum to 14. Now, you're just going to have to trust me when I tell you this next thing. And you might hear me say things like this a lot in the coming week, because I'm going to sound like a broken friggin' record